Deputy NASA Tech Fellows for Guidance, Navigation, and Control, and I'll be moderating today's webcast. The idea to have these hour-long webcasts originated several years ago with members of the NESC, GNC, TDT, or Technical Discipline Team, who thought that this would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. Please note that this webcast is being recorded and will be made available for subsequent viewing on the NESC Academy website by visiting the recording link in the invitation. I'm now very pleased to introduce today's speaker, Dr. Jeb Orr. Jeb is Principal Staff, Flight Systems at McLaurin Aerospace, and he supports commercial space and DoD programs and also serves as a technical specialist for the NASA Smart Marshall Space Flight Center's Control Systems Design and Analysis Branch. It's a little bit of a mouthful. Dr. Orr holds a BSc in Computer Engineering and an MSc and PhD in Controls, all from the University of Alabama in Huntsville. And his research interests include flight dynamics, control allocation, propellant slosh, adaptive systems, and numerical methods. Jeb's talk today is entitled Multiple Effector Control Allocation in Theory and Practice. This talk will present a discussion on improving the capability of current and emerging aerospace systems by the optimal allocation of control effectors. Jeb will discuss the theory of control allocation with applications to aircraft, spacecraft, and launch vehicles, and survey the characteristics of different approaches. As usual, at the end of the talk, I will moderate a 10-minute question and answer period. You can submit questions to Jeb via the chat at any time. I encourage you to submit your questions as they arise rather than waiting to the very end of this webcast. Okay, now I'd like to turn this webcast over to Jeb. Take it away, Jeb.
All right, thank you, Bill, very much for the introduction. We'll go ahead and go to the first slide here. So, so today I'm going to talk about the theory, primarily the theory, and some of the applications, implications, and advantages and gotchas associated with the pretty broad field of control allocation. All right, so what is control allocation? So anyone that has been involved in vehicle design for anything that has more than 1 degree of freedom is well aware that in practical systems, we often have vehicles that are over-actuated that have multiple control effectors. These can be various types of force or moment generating devices ranging from aerosurfaces to factorable nozzles to RCS jets or all kinds of novel control devices. All right. Now, typically for practical reasons, we don't want to do control synthesis or provide control inceptors for every individual surface to a human operator. So we use a control allocation scheme. And what a control allocation scheme does at a mathematical level is it attempts to kind of square things up. And we replace these multiple controls, sometimes in the dozens, with a fewer number of virtual controls that are equal to the controlled degrees of freedom, so that enables us to design the system in a more intuitive way, sometimes using classical control techniques, not necessarily, but sometimes. And a couple of examples where control allocation would be applicable, and I can talk to some of these. Large systems of diverse thrust vector actuators, Space Shuttle is an example that used a kind of an ad hoc control allocation scheme, but had to deal with things like the cant angle of the orbiter SSMEs combined with a wildly different control authority from the boosters and the SSMEs combined together during the ascent phase. The F-18 there, see if I can turn my laser pointer on. So the F-18 there is the fast aircraft, which has now been decommissioned, but used a pretty sophisticated control allocation scheme for some experimental research that was done out at Armstrong. A very sophisticated airplane. I'll talk about the F-18 HARV here in just a few minutes. X-38, another example of a lifting body. Lifting bodies typically have very interesting aerosurface layouts because they're designed, to usually for some sort of orbital entry mission, which has widely ranging aerodynamic characteristics, and so the surface layouts have to adapt to that and also deal with thermal limits and so on. So that's a really interesting, challenging control allocation design problem. And then one that's very close to my heart, I was involved in the design for SLS. And so we'll talk a little bit about the SLS control allocation law and what some of the implications are for large boost vehicles. And so a little bit of background, my area is in the flight dynamics and control design for large rockets. And so while a lot of the examples we'll talk through today involve other systems like aircraft and spacecraft, some of the kind of neat features we'll talk about arise in rocket systems, and we'll use different systems to anchor the discussion. But I will show some more detail on some of the aircraft and rocket problems. All right, so ultimately, what are we trying to do? We're trying to take a large number of controls and reduce the order of those controls so that we can allocate them in some optimal way. And what optimal means is depends on the application. We'll get into that a little bit. Okay, so I think everyone should be ready and brace yourselves for a little bit of mathematics here. Part of the intent of this talk is to focus on the underlying mathematics, not necessarily the algorithmic formulations and how you solve these optimization problems, but more how the problems are structured and what they are from a mathematics and geometry and topology standpoint. So let's talk about, in a simplified way, what are we trying to do? Okay, so if we represent the vehicle dynamics as some just basic nonlinear, non-autonomous set of differential equations, and there's some state vector and some output vector, we'll assume for the purposes of this example that the state vector and the output vector are the same size. And a lot of the problems we'll look at for aircraft, I'll linearize the aircraft dynamics or linearize the rocket dynamics. That's pretty typical. So the structure of the problem and the control design part of the problem in terms of stability theory and control law synthesis is really not what we're too interested in here. So what F contains, what H contains are not that important. Really, what we're going to boil this down to is a linear algebra problem. And then once we've solved the control allocation problem, that simplifies the design for the subsequent control design problem. And the control design problem is not what will be in the scope of the discussion today. So if we just simplify this system down to some either linearization or perturbations around some nominal point, some nominal control position, we can linearize the sensitivity of the system dynamics with respect to changes in the input variable. The input variable here is u, and this u is just a vector of dimension m that will contain the control deflections. All right, so we are restricting the problem here to situations where the response of the dynamical system to the control changes is linear in those changes. All right, so this is typical for many air vehicles as long as the control deflections are not too far from u naught. It's true for the thrust vector controlled vehicles for small perturbations, and it is true for RCS. So this is very applicable. It's not universally applicable. Sometimes this is still a nonlinear function, and there are some other methods in the literature that allow you to deal with that. But to introduce the basic geometry and the restrictions on the problem, we'll just assume that the system is linear in the controls. All right, so this is kind of the B matrix that you see in the usual sense if you have an x dot equal ax plus bu, as you would in a typical linear control synthesis problem. Okay. All right, so we're going to call that the input sensitivity matrix, or it's just a matrix of partial derivatives of the response of the state derivatives with respect to changes in the input. Right. So what that does is we can think about it as a linear map. It's a linear transformation. It maps the actual controls u onto some controlled degrees of freedom. Those controlled degrees of freedom could be the angular accelerations. They could be both lateral and angular accelerations, or they could be some other intermediate control variables. What variables those are is not that important. The key is that B is typically not square. All right, so in a typical, say, aircraft or spacecraft control problem or rocket control problem, the number of control degrees of freedom given by N is typically 2 or 3, like pitch, yaw, and roll. And M is the number of degrees of freedom of the effectors. All right, so in order to proceed with the synthesis technique, whatever technique we're using for control design, we want to replace BU with some virtual control. We'll call it V. And I'll try not to abuse the notation too much. There's been some changes in notation from the aircraft world to the thrust vector world and so on But generally what we'll have is the control deflections or the control input vector is going to be called U, and the virtual control will be called V. All right, and what we're doing here is essentially squaring up the system. Now, for those with a controls background, you'll see here that I don't have a direct feed through term here, meaning the relative degree of the system is at least 1. That's not a restriction in any way. That's just a way that we've simplified this example for discussion. Okay, so you can see I replaced BU on the right-hand side of this equation with V, the virtual control. All right, so what is the control allocation problem? It's finding a unique U, a unique set of controls of all the possible solutions that satisfy V equal BU. So V is prescribed. V is a virtual control that is prescribed for a typical, aircraft rocket type control design. V may be a desired torque or a desired angular acceleration. B is a sensitivity matrix of the changes in control deflections, including the effects of inertia on that angular acceleration. So it's also convenient from a control design standpoint because it helps us normalize some things and put them all in a body frame. And then we can look for, of all the possible perturbations in U that would satisfy V equal BU and get us the V that we want, what is the one that is optimal in some way? Okay, so what optimal means depends very much on the problem. So if we are not constrained, if you can take on any values, then we can frame this as a simple convex optimization problem that says at any given time, minimize some convex function of U subject to the constraint that V equals BU. Well, if B is not square and B is full rank, of course, there are an infinite number of solutions U that satisfy this equation. So we have to introduce an additional measure, convex measure of optimality, in order to pick a unique U from that set. Okay. Now, if the problem is constrained, and typically the problem will be constrained only over some region of V. So that region of V, the virtual controls, where the torque or angular acceleration command cannot be satisfied. And in order to satisfy the command, we have to saturate one of the control effectors, either in angle or rate. Then the structure of the problem changes. And now we have a constrained control allocation problem. Now, of course, we can treat the whole problem as a constrained control allocation problem. And the nature of the solution changes whether the controls are saturated or not. And we'll talk a little bit about that. But the structure, of course, at that point changes. Now we are no longer saying, find the best U of all the possible U's subject to this constraint that V equals BU, but rather we have a constraint on what the admissible values of U are. Now I need to minimize the error, some metric of the error between the V that I achieve and BU, or the V that I commanded and BU, which is the V that I achieve. Okay, so really when we look at the unconstrained problem, this is just a linear inverse problem. It is a simple linear algebra problem. Now, it turns out that because of the constraints, it becomes a relatively complex problem with a lot of caveats and implications of different solution methods, and it has yielded a really rich literature. Okay, so why do we do control allocation rather than MIMO, broad MIMO synthesis in the controls world? Well, it eliminates redundant degrees of freedom. It simplifies our design problem considerably. So while we could use MIMO techniques, if we have a system that has particularly complicated structural dynamics, for example, it is then still possible to look at single loop stability criteria using the Nyquist criterion. So we can still apply all of those linear stability techniques that are very common for flight certification. A lot of practical and classical control laws break the system into 3 uncoupled or 3 degrees of freedom, like roll, pitch, and yaw, that are either uncoupled or have some limited cross coupling, like roll, yaw interconnects. And also, as I mentioned earlier, it would not be reasonable if you have an agile fighter aircraft, for example, with 16 control effectors, to put 16 control inceptors in the cockpit. Pilots are used to operating on 3 degrees of freedom, so we have to have some way to map those 3 degrees of freedom into optimal combinations of the individual control effectors, whatever those optimal combinations are. All right. So as I mentioned, it's straightforward to solve this problem if the moments or accelerations, the virtual controls, are linear controls, or are linear in the control deflections. The controls are unconstrained, And even if they are constrained, if the constraints are geometrically simple, okay, so a very simple constraint function, and I'll get into the geometry of this in just a minute, is just that the absolute deflection of the controls cannot exceed some value. All right, so say these are aero surfaces, it's an aileron, it's limited to plus and minus 10 degrees of deflection in a particular flight condition. Now those deflections can change in time, that's fine. For example, due to thermal limits or structural load limits, what have you. This is a very simple constraint. And it turns out that even if these limits are asymmetric, it doesn't unnecessarily complicate the problem too much. All right. So this basic problem, the formal theory was really first introduced by Wayne Durham and his students at the University of Virginia in the early 1990s, 1993, 1994. A couple of seminal papers in Journal of Guidance, Control, and Dynamics really kickstarted the theory using linear algebra and these mappings. This really developed and blossomed into an advanced field. Of course, the need for these techniques was certainly known before then. There's a lot of work that was done at NASA in the early 80s. There are evidence of formal control allocation methods showing up all the way back into the 1960s and understanding these linear relationships. So, but the evolution of formal approaches to solving this problem really emerged in the early 1990s, and it's blossomed into a pretty rich field since then. A lot of it is focused on how do you solve the problem algorithmically, efficiently in a computer that has smooth characteristics when implemented in time domain, and so on. So let's talk a little bit about examples, motivating examples. So this is F-18 HARV, the high angle of attack research vehicle. This was flown at Armstrong, then Dryden Flight Research Center from 1987 to 1996, and used advanced control allocation to significantly demonstrate expanded capability for this class of aircraft, this class of fighter aircraft, combining thrust vectoring, movable forward strakes, all kinds of really advanced techniques. And control allocation really made this possible. This turns out to be one of kind of the anchor examples in the control allocation field. If you want to test an algorithm on something that has a linear inequality constraint, this is kind of the example that you use because it has some really neat geometric features. And so this shows up quite a bit in the literature. All right, so if we go and get a little bit out of the very general dynamical system description that we used earlier, and say we have just linear perturbations from some operating condition, an angular rate, dynamic pressure, Mach number, alpha, beta, and some control positions. And in the HARV example, the B matrix maps control deflections into normalized aero coefficients. Right, so these are your CM, CY type aero coefficients, and then we can go look at what does this look like geometrically. All right, quite a few control effectors. There's 10. So you'll see in these boxes at the top right, when I talk about these examples, I talk about the number of controlled degrees of freedom, 3, and the number of effector or actuator degrees of freedom, that's 10. So this I call a 10 into 3 problem, which means the B matrix is a 3 by 10 matrix. All right, so the control system is operating on roll, pitch, and yaw rates, and these limits are asymmetric. All right, so it's a little more complicated than just the absolute value of U less than or equal to C. You can see that, for example, the tail and the trailing edge flaps have, positive deflections, negative deflections, and these are not necessarily symmetric. And this doesn't present any particular concern. Okay. All right, another motivating example for spacecraft. Same theory can be applied to spacecraft. So here's Apollo LEM in 6 degrees of freedom. This is a typical, human-rated spacecraft configuration with a significant amount of redundancy in the attitude control system. It's all RCS. So if we look at the nonlinear rotation and translation dynamics, on the right-hand side, we just have the sum over all the jets, R cross F. A in this case is just the unit vector of thrust, and then U is a control vector. And it's a little different here because they can take on only values of 0 or 1. It can either be firing or not firing. And so then we can lump these sums into just a matrix description. So you have M times U and R times U. And now we have, because on LEM you had 4 quads, okay, with 4 jets each. There's a total of 16 jets and 6 controlled degrees of freedom to simultaneously control angular acceleration and translational acceleration. This becomes a 16-into-6 problem. Now, the way this was actually implemented in the LM flight software was with a whole set of different firing tables based on different failure conditions and jet select modes and so on. But for the purposes of discussion, we can solve this problem using a control allocation technique. So we'll use that as an example here in just a few minutes. All right, NASA SLS, which I'm proud to say we flew these algorithms just a few weeks ago, November 16th. This system is a challenging control allocation problem because of the diversity and the number of degrees of freedom that we use for thrust vector control during boost and core stage flight. So right after coming off the pad, we have 2 5-segment solid rocket motors and 4 RS-25 core stage engines. Now, these engines have significantly different thrust. They have different moment arms, and they have different vectoring limits. They also have different vectoring rate limits. And so we account for all of those constraints simultaneously. And in this system, that's done online, which allows us to account for notified faults, for example, the loss of a core stage engine. The other thing that's very important for control allocation algorithms, I'll get into in just a minute, is that when we're selecting an algorithm, it helps to have linearity of that algorithm, meaning using a linear mapping of virtual controls to effector deflections over some range, which allows us to use linear stability analysis techniques. It needs to be deterministic and it needs to be linear, because in the cases that we have a significant amount of control structure interaction, liquid propellant to airframe coupling, or servoelastic concerns, being able to assess those using linear stability analysis techniques is paramount. And that is certainly the case for this vehicle, and is the case for almost all vehicles that are able to achieve orbit because of the structural margins drive low frequency, high gain bending modes and drive us towards using linear techniques. Now, the mathematics is very similar in this case, although the notation is slightly different, so I apologize for the notation change. In this case, U is actually the thrust unit vector. And in control allocation literature for rockets, we use delta, a big delta, to be essentially the individual engine deflections, little delta 1, little delta 2, which are the local pitch and yaw degrees of freedom stacked up together. But you end up with the same type of problem. You have a pseudo control, which is just the angular acceleration. What we'll end up doing is inverting M, this matrix, which maps the effector, the TVC deflections, into torques. We'll invert J, the inertia tensor, we'll pre-multiply by M, and we'll end up with the same matrix B. So if we write M, we're typically talking about torques, and if we write B, we're talking about angular accelerations. But again, that's just a particular structure of the problem. All of these techniques apply for arbitrary pseudo controls, whether we're talking about rockets or spacecraft or UAS, quadcopters. It's the same theory underlying. All right, so what is control allocation algorithmically? Given a desired virtual control, we need to find a U that's optimal. I introduced this just a minute ago. So this is the unconstrained problem, all right? So it does simplify the design problem. There's usually 3 controlled degrees of freedom. And if the solution is unconstrained, there's always a solution for an arbitrary V if B is full rank. Okay, so if B can generate moments in any direction, all of its column vectors, some will be linearly dependent, but if we have a minimum of 3 independent column vectors, then I can always generate moments in any direction. Cases for which that's not true, we call a degenerate geometry or a degenerate control allocation matrix. And there are ways to deal with that. And those can happen, for example, if you lose control effectors, right? But we won't address that in detail here. Again, that solution is not unique. All right, so what does it look like from an autopilot standpoint? All right, so I have what would be typically called a plant model, which is my controlled system. I have some vehicle dynamics in here. I have a sensor that senses some controlled degrees of freedom. In this example, it's just angular rates. So this is like a rate feedback autopilot. And I have a whole bunch of actuators, right? So I'm not ignoring the actuator dynamics. These are very much in here and they're very much part of the analysis. But what my control law does is it generates a requested, say, angular acceleration. And then it's up for my control allocator to decide how to convert that into actuator commands that will achieve that angular acceleration in some optimal way. All right, so the most common way to go about this problem is using what's called a pseudo-inverse solution. All right, and this is kind of the intuitive way. It's not always the best way, but it's very common for a variety of reasons. If the set of controls is unconstrained, we can use a pseudo-inverse. This is a linear least square solution. It does not have any knowledge of the constraints. And what a pseudo-inverse is called formally is called a right generalized inverse. And a generalized inverse is any matrix P that satisfies this identity, where B is the control sensitivity matrix, P is the pseudo-inverse or generalized inverse, and when you multiply the two of those together, you get I. One way to think about that is if I have a command, so if I say VC is my commanded pseudo control or my commanded virtual control, all right, I multiply it by P, I get a U, and that condition holds, then if I put that command into the pseudo inverse and then map it back, I will get what I asked for. So if you look at over here, I've got V, my achieved virtual control, VC is my commanded virtual control. So if BP is equal to I, if I have a pseudo inverse that satisfies this, I will end up getting what I asked for. Now, is this a good idea? Is this necessarily the only answer? No, because there are many more things that I need to be concerned about with you to make sure that I don't just get the command I asked for, but I also do that in some optimal way. All right. Now, as it turns out, a generalized inverse has at most m minus n times n free parameters. That's a lot of parameters. So there are lots and lots of inverses that will satisfy this condition. And I can actually use that in the design to select different ways to solve a control problem. But usually there's far fewer. Okay, so this matrix P, this generalized inverse, is often called an allocator matrix, or sometimes called a ganging matrix for the ad hoc approach of control ganging, either mechanically or in software, say coupling ailerons together left and right in order to get a roll response. Right. So probably the most common generalized inverse that's used for control allocation is called WLS, or the weighted least squares inverse, and it's pretty straightforward. Okay, so what does WLS do? It minimizes the weighted to norm of the control. So that's just a quadratic form, 1/2 U transpose SU, where S is an inverse weighting matrix. Lambda is just a Lagrange multiplier. Okay, so again, this is solving that problem. It says, of all the U's that satisfy V equal BU, find me the one that has the smallest to norm. It makes the problem convex. All right. Now, you can go through and take partial derivatives of H and set them equal to 0 and do some simple algebra, and you'll come up with this form here. It says that P, my allocator matrix, is just WB transpose, BWB transpose inverse. This is used in all kinds of aerospace systems. Now, the problem is it doesn't have any knowledge of the constraints, but it is very easy and intuitive to put together. And as long as the weight matrix and the B matrix are combined in such a way that this value is non-singular, it has a solution. And basically what that says is, as long as I weight my controls in such a way that the control effectiveness doesn't lose rank, I don't take away any controls that preclude me from controlling a given degree of freedom, I can always find a solution. So this is really actually helpful for things like online control reconfiguration, because I can at any point in the software say, hey, the engine controller just told me that this rocket engine shut down, and I'm going to take the 2 TBC degrees of freedom out of the weight matrix for that engine. And as long as this thing is still non-singular, I still have a solution. I can instantly reconfigure that. Now, there's some practical things that have to be dealt with at the boundary when that configuration changes, but for the most part, this is a great way to take controls in and out of the solution in an elegant way. All right. Now, what does this matrix P give you? It gives you n linearly independent columns. Okay, so if the original B matrix has n linearly independent columns, then P will give you n columns. Now, this is very important when we start talking about the null space and the geometry of the constraints. Another thing for the weighted least squares inverse, if you're ever in MATLAB and you type, a backslash operator or PI and V, which are actually very slightly different, but for the weight matrix equal to any scalar multiple of the identity, and that's a formality there. It's really just think about it as if the weight matrix is the identity, this thing collapses down to what's called the Moore-Pedro's inverse, which is what you get if you type PI and V in MATLAB. And that minimizes the unweighted, or just the two norm of the control vector. So this is called the so-called minimum control solution. It just makes the control vector as small as possible. This can be really great if you're trying to preserve power, or holding torque for actuators, or minimize drag, depending on what the configuration is. So that can be very helpful, but it's also not very efficient from a control capability standpoint. But the thing to keep in mind is that in that case, and only in that case, the columns of the allocator, meaning what are the directions in the control space that are allocated, are orthogonal to the null space of B. And that means they don't generate any internal loads. All right, that's an important feature, and we'll talk in just a second about what that means. Okay, so what is the null space? All right, remember B has greater column dimension than row dimension. Okay, so M is greater than N. There has to be a null space B if B is full rank of dimension M minus N. Okay, so for the example of, say, SLS, where we have 3 controlled degrees of freedom and 12 engine degrees of freedom, that means there is say 8 controlled degrees of freedom. There's a null space of dimension 5 in the space of actuators. These are ways that I can move the actuators that generate no net load on the vehicle. One great way to look at that, this is for a very simple case. This is a Titan II GLV, which has 3 controlled degrees of freedom, but 4 actuator degrees of freedom. We can actually visualize exactly what those control vectors are. So if we just do a straight pseudo-inverse solution, what we will find is that we get 3 column vectors in that pseudo-inverse. 1 corresponding to differential motion of the engines for roll, 1 corresponding to symmetric pitch motion of the engines for pitch, 1 corresponding to symmetric yaw motion of the engines for yaw. Now there is a third, or a fourth direction in this space of dimension 4 that is in the null space of the B matrix, and it is inboard outboard motion of the engines. So in terms of mapping into angular accelerations, if I deflect the engines inboard or outboard towards one another, I don't generate any net moment. And that is a solution where B times U for any scalar multiple of that vector is equal to 0. That's the definition of the null space. Now it turns out the null space is pretty useful. All right, so in control allocation, there's this concept of the attainable moment set. And it's really just a set of linear inequalities. Now this is a little more complex when the constraints are not saturation constraints, when they're coupled together, for example, in the case of ellipses or other nonlinear manifolds. But for most of the control allocation literature, we just write the limits in terms of the control vector, and it's just some row of this A matrix transpose times U less than or equal to a constant. All right, so to get into the geometry a little bit, each of these expressions defines a half space in an m-dimensional space. That m-dimensional space is the size of the controls. So you can just think about the equality relationship here. So like A transpose J times U equal to C defines a plane, and the inequality defines everything that's on one side of that plane. And so if I have symmetric limits, for example, I have 2 of those planes facing each other. Those 2 half spaces intersected give me a convex set that contains my admissible controls. All right, so there's always 2 M inequalities, and this forms a thing that is called a polytope. Now it's convex, it's closed and bounded, and the neat thing about linear transformations is if I have a closed and bounded convex set in a space of dimension M, and I multiply it by B, or it's transformed by B, it maps into a closed and bounded convex set in an n-dimensional space, and that's the, say, 3-dimensional space of angular accelerations. All right, so the set of all possible controls generally we refer to as omega, and this is an example with a linear inequality constraint, just AU less than or equal to C. It's called the admissible set. It's the set of all possible controls. It has an image in 3-dimensional space or n-dimensional space that is preserved. This boundary is preserved. Some of it is projected inside, but some of it gets projected into this exterior boundary. Okay, this set is called the attainable moment set, and this is very important in control allocation theory. It represents the extents of what a given set of controls can do subject to the constraints. That is a theoretical upper bound. And a very important relationship from control allocation theory is that it's actually very difficult to achieve all this. Using most simple algorithms, you can usually only get part of it. You can't get all of it. So, but the idea is that any point in or on this boundary, this is say in angular acceleration, there must be theoretically some point over here that satisfies the constraints and generates that moment. Now, whether I can get it online with an algorithm is a different issue. All right. Okay. So constraint control allocation, what do? We have a desired virtual control. We want to find a U that's close to the desired moment in some sense. So if we formulate this as a convex optimization problem, say on the 2 norm of my desired command minus my achieved response, this is just a standard optimization problem. It's a QP or quadratic program, right? So it's a quadratic objective function and a linear inequality constraint. That's great. This is actually not a really good one for practical control laws because minimizing this does not guarantee collinearity. All right, so I can make this thing really small, but V and BU don't necessarily point in the same direction. And for controls engineers, that leads to cross-axis coupling, which is undesirable. So Wayne Durham in 1993, circa 1993, 1994, framed this as a geometry problem and came up with this algorithm that he called direct. And it says, you know, make my objective function just a scalar alpha and find an alpha that is as large as possible and a vector U such that this is satisfied. So what it does is it essentially takes the image of the constraint and makes it as large as possible. So it finds the boundary of the constraint and then scales it back to be a response that's collinear with what you asked for. Now this helps, but it's not very computationally efficient. It turns out that it can be recast as a linear program and solved online using a simplex algorithm. Simplex is a very simple algorithmic technique used to solve LPs. It works very well. Unfortunately, while it does guarantee, it's the only algorithm, or one of the only algorithms, that guarantees that you can access all of the theoretical capability. It's not very efficient because it turns out that most of this boundary is intersected with the null space. So while you can achieve the exterior limits of the attainable moment set, you're actually wasting a lot of control power in its interior, which is not necessarily efficient. There are many other algorithms for doing this. They all have their own advantages and drawbacks. And unfortunately, we don't have time today to go into a lot of them. All right, so why not just use weighted least squares for everything? Okay, this is a key result in control allocation theory. It's universal, it's very important, and it's very counterintuitive. But it was originally proved in the early 1990s by Durham. A generalized inverse cannot access all of the moments. Okay, so if I look at, say, what is the control capability of a set of vectored engines, and I map that over here, I look at the image of the attainable moment. So what is the angular acceleration contribution of each of these guys? And I map them into 3-dimensional space, I will get this thing called the attainable moment set, which is the total capability. If I then use any linear inverse to allocate those controls, I'm confined to what is called a proper subset. So there will always be part of this space in 3-dimensional space that I cannot access without changing the direction in a nonlinear way. So a linear control allocator or a pseudo-inverse solution has many advantages in terms of things like structural loads and being able to control the null space and things like that. But there's always part of the system that I cannot access. This is very important. This example over here on the right is a trivial example that I constructed where the B matrix is basically just a couple of ones, and the constraint, it's 3 controls, it's 3 into 2 problems. There's 3 controls into 2 objectives. So we're mapping a 3-dimensional cube with limits plus and minus 1 onto a plane. And as you can see, what the pseudo inverse does, if you look at this and just kind of turn your head just right, you can see this is actually just a projection of a 3D cube into a 2D space. Now, as it turns out, we can play with the inverse parameters all we want, and we can make this projection fit the theoretical upper bound pretty closely, but there's always going to be some area left over. And that was proved by Durham. It's very important. So the takeaway from this is in order to access all of the attainable moments, you have to use a nonlinear, usually iterative algorithm. But that's only really required at the exterior regions of the boundary. So most practical control allocation algorithms, they use a linear transformation in the interior, and then they switch to a nonlinear mapping in the exterior. And so when we talk about how effective or efficient a control allocator is, if we use the term efficiency, sometimes what we're talking about is what is the area of the achievable moments versus what is the total theoretical upper bound. And we can do that in terms of either volume, or we can project it into pitch yaw, for example. So there's lots of ways to define that, but typically we're talking about allocated volume. How much volume can we access of angular accelerations versus how much volume is theoretically available. All right, so here's an example using the classic HARV case. Okay, linearization. This is right out of one of the most popular control allocation examples in the literature. 10,000 feet, Mach 0.3, relatively high alpha, no side slip. Okay, so everything's nice and symmetric down the down the longitudinal plane. This is the moment matrix. Okay, it's a 3x10 matrix. And if we apply these limits and we look at what the shape of the attainable moment subset is, you see it has this nice symmetric shape. All right. If we use a straight Moore-Penrose inverse, we only access 13% of the total volume. So this is where even getting deep into the theory, a takeaway even at the system engineering level is if the design doesn't close, the first question to ask is, are the controls being allocated effectively? Because sometimes ganging approaches or pseudo controls approaches are very simple, Moore-Penrose inverse, least squares. This is not readily apparent unless you go do the analysis. And so sometimes there's hidden capability in the system that can be eked out using nonlinear approaches. All right, let's look at what does this look like in a spacecraft situation. Okay. This is, again, the Apollo LM, a very specific configuration for which I have data. It's Apollo 12 pre-PDI. So usually the way we can handle this for control allocation for RCS is, since we're confined to just turning the jet on and off, we actually convert this to a problem in time. And we use exactly the same algorithm, same mathematics to solve for this in time. So what we do is we just multiply the angular acceleration by some base frame rate. In the case of the production LM, this was 100 milliseconds, autopilot executing at 10 hertz. Okay, and so now we convert the problem from an angular acceleration problem into a rate increment problem. So we have, from the autopilot or from the pilot interface, a commanded rate increment. Over here on the right-hand side, we have the jet location, the nominal jet force, and the jet unit vector A. And the control vector then becomes a vector of on times. And so at each minor frame cycle, we then send delta on time commands to a jet controller, which will provide a pulse of the desired on time to each jet. And there are various ways to handle the minimum on time issue. If the jet firing command is below the minimum on time, we may not fire at all. We may scale the times to account for the fact that at very low on-time commands, the jet response is not a pulse, not a square wave. Or these on-times can be redistributed, for example, into other jets. So there's various ways to deal with that. But the simple, kind of not that efficient solution that works is just, if they're below the minimum impulse bit, they just get clipped, and this turns out to work pretty well. Okay. The other thing that's kind of neat about this, so this is that problem for the LM scaled into rate increments, and you can see at this configuration, there's about in a 100 millisecond frame, there's about a ½ degree per second of increment that can be delivered by the full 16 jet configuration. It's pretty good. It's a lot of control authority. The same techniques can be applied for certain selections of jets to determine what the minimum rate increment is, and that helps for jet sizing. So if you were to imagine that being plotted, it would be a very small minimum increment here in the interior of this domain. And that helps us do things like size what the limit cycle amplitude is going to be with a given jet size. Okay, last example, space launch system. So space launch system used a relatively sophisticated online weighted least squares allocator. It's exactly the same expression that I showed you earlier that we derived just using a convex constraint, or a convex objective function, and a Lagrange multiplier. The weighting is optimized to maximize the pitch yaw authority. Okay, it's computed online, and that allows the system to be able to accommodate in real time things like an engine out that's notified. The engine controller says, "Hey, I'm shutting down this engine." We can say, "Okay, well, I can't get any thrust out of that engine anymore. I can't vector that engine anymore, so I'm take it out of the solution." And that's done with no net change in the forward control gain. So the stability margins remain the same within reason. This is really, really neat for analysis. Okay. Fundamentally, the constraints here are circular or elliptical in the general case. And so the geometry is a little different than we have in the aircraft problem. And you can actually define this as what's called a QCQP, or a quadratically constrained quadratic program. But we don't solve it as a QCQP because a QCQP is iterative. The solutions are not necessarily guaranteed to be smooth in the input parameters, right? So as I change the command, I could get different solutions. And linearity is required, at least in the interior, for control structure analysis. But what we're able to find with the SLS geometry is that we can adjust the weighting of a weighted least squares allocator. And this is common for WLS allocators. You can actually do, if you get smart about how you do the weighting, you can actually recover quite a bit of the total capability. And so what we're looking at here is projection of pitch and roll, okay, and pitch and yaw. And so what you see is we achieve the theoretical maximum possible pitch and yaw authority when we don't have a roll command. And as we go up into the higher roll commands, we give up just a little bit of the pitch and yaw authority, all right, over the theoretical maximum. And so that's a very intentional design choice. And that's kind of a common weighting for a rocket system. All right, so some more advanced topics. We don't have a lot of time to go in. This is just one slide on this. I mentioned that the weighted least squares allocator does not address saturation, and it does not directly address rate limiting. And the issue here is that a change, if you get to the boundary, you say I saturate one of my aero surfaces, or I saturate, one elevon, and so the actuator controller says I'm not going to command it any further, and it just holds a position, and all the other actuators continue to move. Well, what has that done? In the m-dimensional space that contains U has changed direction, which means that V is no longer equal to BU. BP is no longer equal to I, and I get cross-axis coupling, right? So that shows up as a cross-axis coupled response in the control. Immensely elegant, but we just find a scale factor that scales the entire command to keep the response in the boundary. And that way you give up a little bit of authority, but you're able to maintain collinearity of the response and the command. And this tends to work really well in applications. The other thing you can do is you can divide the control allocation problem into many smaller control allocation problems over the maximum deflection that a control effector could move in a single time step and actually get rate limiting. And so again, SLS is an example. It's a non-trivial geometry because they're all circular. But what we're able to do is do what's called coordinated rate limiting, where in the event that a single actuator saturates in rate, we actually scale back the rates of all the other actuators so that we get a coordinated response. Everything stays in the range space of the allocator, and we don't get undesirable cross-axis coupling. And this works really well in practice. All right. So that's a lot of information, a lot of theory in a very short amount of time. But what I want to summarize, I haven't, of course, gone into the huge diversity of control allocation algorithms. Null space projection, null space augmentation, cascaded generalized inverses, sometimes called CGI, or redistributed pseudo inverses are very popular. There are various ways to construct the weight matrices to do things like handle uncertainty and aerodynamic coefficients. So there's a rich literature out there of things that can be done very intelligently with control allocation. Daisy chaining for handling diverse types of control effectors sometimes is a dangerous thing to do. Sometimes it works really well. This is going to continue to be a rich topic for emerging aerospace systems. So all the examples that we looked at today, plus of course, over-actuated electric aircraft that have many separate propulsive devices that can be individually commanded, unmanned aircraft systems, tailless aircraft, novel spacecraft designs that combine, wheels and control moment gyros, for example. All of these techniques can be applied to those systems. And also control of multiple objectives like structural loads and drag. There's a lot of work in drag minimization control for crews using control allocation. All right. There are, again, many algorithms. Some have somewhat dangerous caveats. Some are intuitive, some are non-intuitive, some are very elegant, but difficult to implement computationally. So I would encourage you to take a look at there's a lot of really good literature on this, and I'm certainly open if anyone's looking for a particular solution to a particular problem. I may be able to help point folks in the right direction. All right. And the last thing I'll say in summary, I mentioned this before. If the design doesn't close, and this comes from personal programming experience, if the design doesn't close before changing the OML to get better control moment response from the aero surface effectors, make sure that the algorithm is taking full advantage of the available control authority, because sometimes it's just a matter of better and more efficiently weighting the control allocation solution before you go off and move hinge lines around for ailerons and so on. All right, so I'll wrap up there and turn it back over to Bill.
Hey, Jeb, thanks. That was a really great presentation. And thank you for sharing all that information. Yes, and clapping all around. So, oh, I should turn my camera back on. Okay, so we had one question in the chat, and this is from Jingpei. It looks like we just got another one that popped up. Okay, so this is from Jing. Do you have any references and examples where the designer used a linear allocator for the interior and then used a nonlinear allocator to get the AMS near the boundary?
Yes. So there are, I would say cascaded generalized inverse is an example of that. So any solution that uses CGI is an example of that. Now CGI has some problems. And what a CGI does is you do the initial allocation using just a straight generalized inverse. And then if there's a control that is clipped, you take the control, you set it to the value, the saturated value, you take its moment contribution out of V, you remove its column from the V matrix, and you solve the problem again. Now that has some issues because once you've saturated a control effector, you're kind of stuck with it. And so the early decisions in the algorithm can lead to it not accessing the full set of attainable moments, but it is used in a handful of cases. There are other solutions that use null projection, what's called null projection, which takes the difference between the saturated vector and the commanded effector positions that would exceed the boundary of admissible controls, and it tries to get that back by putting that component back in the null space. We actually looked at that for SLS and found it was very effective, but because we had sufficient margin control authority, it did not, the additional flight software complexity to implement it was not justified. So there are definitely a couple of examples of this, both aircraft and rocket domains.
Awesome, thanks for the very thorough response. Okay, so we have another question, and I apologize if I don't pronounce this person's name properly, but it's from Tanavi Nakamura Zimmerer. Can you comment on the usefulness of control allocation in fully autonomous flight control?
I think that it has I think that the value of control allocation universally is to simplify the design problem, right, and allow the autopilot guidance, the integrated GNC system design to proceed in a traditional multi-loop fashion. All right, so we can go after a 24 input UAS control design using a very sophisticated MIMO synthesis technique, but then how do we handle fault tolerance and reconfiguration in the event of an actuator fault? If we were to do that with a 3-loop design and a 24/3 control allocator, it may be as simple as, hey, I'm not seeing any current going to this actuator anymore, so I'm going to take it out of the weight matrix, and then the rest of the design is transparent and the performance is only slightly degraded. So in terms of being able to handle fault tolerance and being able to handle variable uncertainties and control effectiveness and various rate limits and things in a simple, elegant way, I think control allocation is very valuable even for unmanned systems.
Great. And actually, I have a question, Jeb. So the examples you cited were all for basically rigid body control. Obviously SLS, liquid propellant vehicle with lots of slosh. It's a very, lots of bending modes going on. Were you applying this control allocation technique to handle those modes as well? Or was it just assumed that because this is a contingency type scenario, if we maintain control of rigid body, we're not going to overly concern ourselves with slosh and bending?
That's a very good question. So in a design such as SLS or generally for flexible structures now, usually the elastic load or the elastic deformation or the other degrees of freedom are not part of the controlled objective function. They're not part of the directly controlled degrees of freedom, right? But they are absolutely part of the analysis. And one of the very important things about something like SLS is if we think about roll control of the vehicle, whether I vector the inboard engines for roll or the outboard engines for roll, the vectoring that gives me the same rigid body moment may give me a drastically different bending response and torsion, right? So that response is quantified by the frequency domain analysis with a particular control allocator, and that shapes the design or the weighting decisions, right? So I may look at the frequency response and say, hey, I'd love to do all my roll control using the boosters, but I'm going to twist the vehicle. And so yes, so to answer your question, it's kind of a hybrid answer. Mathematically, the elastic response is not a controlled degree of freedom, but the analysis directly informs the choice of weight matrix and the requirement for that mapping to be linear so that we can assess the effect on loads. Now, all that said, there has been work in the NASA community and elsewhere on structural load minimization, direct structural load minimization using control allocation, and that's been applied to transport aircraft.
Excellent, thanks for the answer. So we got another one. Can you comment on how easily these and this is from Spencer Folk. Can you comment on how easily these concepts, e.g. reconfiguration due to faults, may be applied to the under-actuated case?
In the under-actuated case, the mathematics are very similar. It depends on how you consider satisfying the objective, right? Are you trying to do the best you can in a norm sense? If so, the under-actuated case is just for the pseudo-inverse solution, it's just a left generalized inverse instead of a right generalized inverse. And so what the weight matrix means and what the objective function means are a little bit different. But the mathematics are very, very similar. If you look at just a textbook example on the generalized inverses, you can see what they sometimes call a short fat inverses versus a tall skinny inverse. The dimensions of the B matrix are different, and it's more of an optimization estimation problem formulation versus a control allocation formulation, but the implications are very similar. Now, under actuation is tricky because which degree of freedom do you want to throw away, right? Is it 1 degree of freedom or a combined degree of freedom? It depends entirely on the rank of the B matrix. Maybe you have no roll control. Maybe you have control on 2 degrees of freedom, but they're mixed, right? So they project into a subspace that's a plane that is not necessarily in your body axes. So there are some implications there. Hopefully that answered your question.
Thanks again. So I think we're about at the end of our time here. So I'm going to go ahead and wrap this one up. Thanks everybody for dialing in. Thanks especially to Jeb for answering the questions and providing this really excellent talk. So with that, I just want to let everybody know, as always, we are soliciting feedback on this particular webcast and also on the series of NESC GNC webcasts. Shortly, an email will be sent out to all the registered audience participants, providing a link to our brief but hopefully simple online survey form so we can collect your feedback. The email will provide the link where today's recorded webcast can be viewed online in the near future. And the webcast planning committee is always looking for ideas for future webcasts. So that would be of general interest to the GNC community practice. So if you have ideas for other relevant GNC webcast topics, please contact Neil or me or any of the other deputies. And thank you for participating with us today. I hope you can join us again at our next GNC webcast event. And that completes today's NESC GNC webcast. So goodbye for now.